I watched the game. Are they
You guys good? Okay. Do you guys remember Avogadro? We're like hearing that name at some point before. Avogadro is the guy who's famous for his number. His number was like 6.02 times 10 to the 23. That's how many atoms there are in a mole. Does that make sense? He basically was able to calculate the idea that let's not count particles one at a time. Counting particles one at a time is ridiculous. Let's count them in a group at a time. When I teach this to my grade 10s especially, and I'm sure I gave the same analogy to you guys, I like to talk about like going and buying donuts or eggs. You don't actually go to the store and say, hi, I'd like 7 eggs. Does that make sense? That's just not how we operate. You go and you say, I want 2 dozen. Okay? And then everybody hopefully knows that 2 dozen means you actually want 24. Does that make sense? In chemistry, we have a similar concept, the concept being that you don't ever work with one atom at a time. We work with lots of atoms at a time. We work with a mole of atoms at a time. And then we have a way of converting moles into grams using our periodic table. Does that sound familiar? Okay. Well, one of the things that Avogadro was also known for, maybe less famously, but he had a famous proposal. And this is very wordy, so let me read it out first, and I'll try to put it into people words. So, equal volumes of gas at the same pressure and same temperature must have equal numbers of molecules. So, let me try to draw a picture here to help explain this. Let's say that you have a container, and let's say that this container is 1 liter. Okay. And let's say that, just to make things simple, let's say that we did SATP. So do you guys remember SATP means that it's 25 degrees Celsius and 100 kilopascals. And let's say that this is nitrogen gas. Now, Avogadro wasn't actually counting them out one at a time. He was counting them out in large groups at a time. But just for the sake of this picture, why don't I draw 1, 2, 3, 4 molecules? Does that make sense? I know there's definitely not 4 molecules just in the container like that. There's probably billions of molecules, right? But, yeah. Well, his proposal was that if you had another container, it was also 1 liter, it was also 25 degrees Celsius, it was also 100 kPa, but rather than being nitrogen gas, it was oxygen gas. His proposal was for it to have that temperature and that pressure and that liter. It didn't matter what it was. His proposal was gas is gas. He figured there better be also 4 molecules of oxygen in there. That was his idea. So it doesn't matter whether it's nitrogen gas or oxygen gas or carbon dioxide gas or methane gas. If you kind of want to abbreviate his idea, I guess you could say it like this. Gas is gas. I don't care what type it is. It all has the same properties. That makes sense? I guess maybe just extending this picture here. This has, rather than do molecules, why don't I say this one has 4 moles of nitrogen gas? And this one also has 4 moles of oxygen gas. That was his proposal. To be honest, I shouldn't even call it proposal. This is true. We've found out that this seems to be true. He experimentally discovered it over and over and over again. It is true. There is one difference between the two. Although they both have the same number of molecules, they weigh something different. Let me say that again. Even though both of these containers under the same conditions have the same number of molecules, they each weigh something different. And that's because nitrogen is slightly lighter than oxygen is. So even though they have the same number of moles or atoms or whatever you want to say, they do weigh something different. Because nitrogen is 14 14.02. No, 14.01 grams per mole, and oxygen is 16.00 grams per mole. So you would expect the oxygen container to be heavier. Does that make sense though? Okay. So hopefully that puts it into like people words for you. All right, so this leads to a couple of new types of questions we can solve. And they kind of go back sometimes, not all questions, but they sometimes go back to some skills that I've actually already shown you in previous units. And this would be a type of question that we've actually already kind of done this sort of skill. So let me walk you through this one. Let's say that you wanted to predict the volume of oxygen needed to combust C4H10. By the way, anybody know what C4H10 is? It's fine if you don't. I wouldn't expect you to. I was just curious. It's butane. We're going to use butane in one of our labs, actually. So it's very hard for me to get a hold of gases that we can use. So one of the gases I use is butane gas out of like a lighter. That makes sense. So let's say that you were to actually use the lighter and like make it spark a flame. What's actually happening is the C4H10 as a gas is combining with oxygen as a gas and combusting. So this is a skill you guys have worked on previously. What's it going to make?
CO2.
Yeah, CO2 and water. Does that make sense so far? All right, next up we have to balance this thing though, because it's not balanced, and that's very instrumental first thing I teach you when you're in grade 10 kind of thing. 4 carbons to 1 carbon, so I'll throw a 4 there. 10 hydrogens, but they come in groups of 2 over here, so you're going to want a 5 there. Hopefully you guys have seen this scenario before. The oxygens are not going to work out nicely because you're going to get 8 oxygens here and 5 there, which gives 13. Ugh, come on, Chris. 13 oxygens. So do you guys remember how to solve this problem? Yeah, you double everything. So put like a 2 there, an 8 here.
Attention teachers, this is a lockdown. Please secure your rooms. This is a lockdown. Please secure your rooms.
All right. Where were we? I think we were halfway through writing an equation. I don't think I finished balancing though, did I?
No.
Because I'm pretty sure I need to throw the 13 in front of oxygen. Is everybody okay though, like being able to balance an equation at this point in their chemistry careers?
Yeah.
I hope so. I don't mean to be mean, but like that is a pretty fundamental skill. So, okay. Here's the point then that Avogadro had. If you have, say, 120 milliliters of butane, we can actually predict how much volume of oxygen would be required for this to work. And it's really based on the fact that equal volumes of gases have equal number of molecules. Okay. If you have 2 molecules of this, you're going to need 13 molecules of this. Does that make sense? Or if you have 2 moles of this, you need 13 moles of this. Well, Avogadro realized that molecules or moles are really kind of equivalent to a volume. And so here's how I'm going to suggest we solve this then. I would say there's 120 milliliters of C4H10. We don't actually want to know about C4H10 anymore though. So I'm going to put C4H10 on the bottom of a fraction. And the thing that I would like to solve for is oxygen. I'm going to put that on the top of the fraction. I'm going to use a ratio is basically what I'm doing to solve. Kind of like how you guys convert, like, say, kilopascals into millimeters of mercury. The only question then is, well, what's the relationship between oxygen and butane? You'd say, well, there's 13 of these for every 2 of these. Does that make sense where I kind of pulled those numbers from? For every 2 moles of this, there's 13 moles of this. Or for every 2 liters of this, there's 13 liters of this. There's just a relationship between these guys. So that will cancel. So I need you to take 120 and times by 13 over 2. I got 780. It means that there's 780 milliliters, because that's the unit that I didn't get rid of. And then the remaining variable that's left, I guess, is oxygen. That's how much oxygen you would need. I like to think of it as a recipe. Kind of like how when you make cookies, you need 1 part flour, 2 parts sugar, 3 part eggs, something like that. I mean, that's not how cookies get made, obviously, right? But for every 2 of these, you need 13 of these. So if you have 120 milliliters of this stuff, you're going to need a lot more volume of oxygen to make it work. Does that make sense? In a way, to go from 2 to 13 is like timesing by 6.5. Well, 13 divided by 2, what I'm doing right here, is essentially timesing by 6.5. Let me add an extra question to this. So, like, new question. How many milliliters of CO2 gas will be made? Like a follow-up question. To some degree, we've kind of done this already, actually, in the first unit. Do you guys remember the idea of, like, let me just make a new slide here. Now, how if I give you, like, CaOH2, and it dissociated into Ca2 plus and OH minus, but there's, like, 2 OH minuses. If this was, like, say, 1 mole per liter, this was also 1 mole per liter, but this guy would be 2 moles per liter, just based on the fact that you're going from 1 to 2. Do you guys recall that concept? That's essentially, that's the same principle that I'm trying to apply here, is that in this relationship, this is 2. Let's say we're going to carbon dioxide. How do you get from 2 to 8? What do you have to do? Multiply by 4, yeah. And multiplying by 4, if I take 120 and multiply by 4, I'm going to expect that you're going to need about 480 milliliters of this stuff. Just purely based on the fact that this to this is 4 times as big. Does that make sense? How do you get from 2 and get to 10? Multiply by 5. So if you started with 120 and you multiply by 5, that actually makes this guy become 600 milliliters. I like to show that like this, though. I like to teach ratio skills because I find that they're beneficial the more you go into chemistry. So I might say this. You have 120 milliliters of C4H10. Let's say you wanted to find out about carbon dioxide. Then on the bottom of the ratio, I would put C4H10 so that it would cancel. And then the only thing you're lacking then is, well, what is the relationship between carbon dioxide and that's butane? So go back up to the equation. For every 8 carbon dioxides, you need 2 C4H10s. Isn't 8 over 2, though, just 4? So really, like, you're taking 120, you're timesing by 4, so it should give you 480 milliliters because the milliliter didn't cancel. And then if you want to know what type of gas it is, the CO2 is the gas type that is not canceled out as well. That's a good way of showing it. You think about all of that? Okay. That is essentially Avogadro's idea. So going back to this first picture, equal volumes must have equal molecules. Well, if these things right here, in a way, kind of refer to molecules, it can also refer to a recipe for liters as well, for volumes. So we can use kind of this ratio concept to solve a question. So, eventually someone fairly clever managed to figure out a way to kind of expand Avogadro's theory to not have just an equal amounts of moles, but he was able to figure out a molar volume, which basically refers to, like, it doesn't matter what gas we're talking about. All gases should have the same volume depending on how many molecules are inside. So I have a couple of numbers I need you guys to write down somewhere. Do you guys remember STP? Standard temperature and pressure? Someone really clever figured out that at STP, 1 mole should be 22.4 liters. So I might write it down like this. At STP, 1 mole is 22.4 liters. It does not matter what gas it is. If it's hydrogen gas, helium gas, nitrogen gas, it doesn't matter. If you have a mole of it, that's how much room it should require. And probably the same person who figured that out figured out that at SATP, a mole is actually going to require a different amount of volume. It actually requires 24.8 liters. Can anyone suggest a reason why SATP is going to require a little bit more volume than STP? Why was SATP developed? Why didn't we just stick with STP? It's too cold, yeah. We used SATP because it was warmer. Well, what happened to gases when you warm them up? They expand, and they take up more space. So if you had a mole of gas, right, you measured out 6.02 times 10 to the 23, you could actually measure out exactly 6.02 particles. Right? If it was at STP conditions, it would take up this amount of room, but if it's at SATP conditions, it's actually going to require a little bit more amount of space. These numbers here then can help us solve some more complicated problems, and I'm going to kind of combine the last few topics together in some questions. So I got 2 questions, I believe. You guys know helium? You breathe it in, it like makes your voice all high. Has to do with the fact that it's way less dense than air. It just changes the way your vocal cords work. We put it in balloons. So let's say that you have 3.50 grams of helium. My question might be then, how much space will it require? So here's how I'd go about solving this question. 3.50 grams, I'm going to write down helium. I'm going to start with this. And I really, really like to encourage use ratios. Do we want to solve for grams? No. What do we really want to solve for? Well, it says volume, so either liters or milliliters would work. Okay. So what I might recommend is let's write a ratio, and on the bottom I'm going to write out grams, because that grams will cancel. I would love to put liters on top. Here's the only problem. I don't actually have a ratio for you guys that is a ratio between grams and liters. But we do have a different ratio we can use as a go-between. We can use moles. Moles and grams. Michael's looking at the periodic table. You need to use a molar mass to figure this out. What's helium's molar mass?
4.00.
That's probably sufficient. Yeah, the molar mass of helium is 4.00. Does that make sense so far? Okay, because the way molar masses work is that that's how many grams there are in 1 mole. Makes sense. It's on the bottom because I needed it to cancel this grams right here. I'm not done yet though. I didn't want moles, right? So I'm going to write a second ratio, and I'm going to put moles on the bottom and say I never really wanted moles in the first place. I only dealt with it because I needed it. What we really wanted was liters. However, just one slide back, I gave you guys a relationship that someone managed to figure out at SATP how many liters a mole of gas requires. We don't care what gas it is. Do you guys remember that number from a slide ago? There are 24.8 liters in 1 mole of gas, regardless of what gas it is. You guys visualize how this kind of works then? This grams cancels with this grams. As an in-between, we had to put moles on top, because that's the best we could do. But this moles can cancel with this moles and gets us liters. So what you have to do then in your calculator is you have to take 3.50. If you want to, you could times by 1, but that's kind of dumb. So I would just take 3.50 and divide by 4, and then times by 24.8. You could also divide by 1 if you want, but does it make sense when I say that timesing and dividing by 1 is kind of pointless? Because does it change it when you times or divide by 1? So in your calculator, do 3.50 divide by 4 times by 24.8. That's what I got to. And then just to kind of finish off the details and make sure we have it right, what unit is the unit that wasn't canceled? Liters. And the type of gas we're talking about? Helium, because those are the two things we didn't cancel. Does that make sense? What I'm interested to you guys today then is a way of trying to take gases and figure out how heavy they are. Because I mentioned this back on one of my very first slides here. Avogadro's idea was that equal volumes, equal temperatures, equal pressures, they have the same moles. The problem, though, is that each gas has a slightly different weight, depending on how heavy those molecules are. Ultimately, all of these gas molecules are very light, because they're all very, very small molecules. But they still do weigh something. Does that make sense? That's why gravity affects them. That's why we have an atmosphere. And depending on how heavy they are, depends on how much mass they'll require. So now we have a bridge. We have a way to now work with masses. Let me do one more example. This one kind of combines everything we've learned today then into one big example. This is probably the hardest kind of question I can do. We want to determine the mass. So I'm just pausing for a second here. If we're looking for the mass, by the time we're done doing all this ratio type stuff, grams had better be the thing we solve for. That makes sense. We want to find the grams of methane gas. Do you guys know methane's formula? CH4. I also tell you that we're combusting at SATP conditions. And I'm going to give you only one number to work with. 25 liters of carbon dioxide. These questions, if I give you a question like this, is going to seem very, it is challenging, but it's going to seem very daunting at first because you're going to get one number. And you're going to look at this and go, how in the world do I solve a question when I give you just one number? Does that make sense? So I would definitely put a big star next to this because this is kind of like, this is one of the pinnacle kind of questions that I'm going to give you. This will be the challenging one. Okay, before you do anything, we need to write an equation. So methane is CH4, and it says it was being combusted again. So just like we did on the previous example, we should write an equation that says this is what happens. And we need to balance as well. So I have a balanced equation. Are we okay with being able to handle that step? Okay, here's the challenging part. We were given information in liters of carbon dioxide. So like, as a way I could write this is, the starting information I was given was liters of CO2. That's supposed to be start, by the way. And for finish, by the time I'm done, I want to somehow get grams of CH4. So I've got two issues. One issue is I have to convert the type of unit. The second issue is I have to convert the type of gas. So again, I'm a big fan though of, let's use unit conversions. So I'm going to start out by writing 25 liters of CO2. I don't want to work with CO2 anymore. I'm getting kind of tired of that. So let's put CO2 on the bottom. Because we don't want to know about CO2. The question asked us to find out information about CH4. Okay, I got to throw some more numbers in though, right? So what's the relationship between CH4 and CO2? Well, for every one CH4, you make two CO2s. That makes sense? That's what I needed to balance the equation for. Wait, no. No, I screwed that up. That's 1 to 1, isn't it? Hello. You looking for someone in particular?
You.
Oh, what's up?
If you're teaching right now, I can grab you later.
Can I find you later? Okay.
Yeah.
Sorry, I screwed that up. 1 over 1. Does that make sense, though? If I was looking for oxygen, it would have been a 2, but I clearly made a mistake there. So would it make sense then that this CO2 unit and this CO2 unit cancel? Right. In a way, we're kind of like halfway done. One of our issues was we had to convert CO2 to CH4, and we've done that. Another issue, though, is that our unit is still in liters. And I don't want my unit to be in liters. So I'm going to write out a ratio, and I'm going to put a liter on the bottom, because that would cancel out the liter that I have up top here. What am I looking for, though? Grams. Now, don't write this out, but if we knew a grams to liter ratio, I would use it. I don't have a grams to liter ratio, unfortunately. But I do know a moles liter ratio. You kind of have to use moles as like a go-between. And that ratio comes from the fact that we know SATP, a relationship. We just used it a slide ago. In 1 mole of gas, there are 24.8 liters. Does that make sense? Well, if I do that, now this liter back here cancels with this liter over here. So I'm getting closer. At this point here, I have CH4, which is what I wanted. I've gotten rid of liters, but I'm not into grams, I'm into moles. So again, write a fraction where moles is on the bottom, so it cancels. And we actually wanted grams, so put grams on the top. Where do I find a grams over mole relationship? Molar mass. So I kind of have to go to the side here for a second now. We're talking about CH4. So carbon is 12.01. And hydrogen is 1.01, but you need 4 of them. So you got to find a molar mass for CH4. Everybody able to kind of make that step go together? Well, that is how many grams are in 1 mole. So the 16.05 goes on the top, and technically like a 1 goes on the bottom. Now, I've mentioned this already today. I'll say this a lot. Do you actually have to times and divide by all the 1s that are showing up in your equation? That's not useful. But what hopefully you can visualize now is that your liters have canceled, your CO2s have canceled, this mole right here has canceled. By the time you're done, the unit that is left is grams, which is what we wanted. The gas type that is left is CH4. So all we have to do is do some math now. So I'm going to say let's take 25, let's divide by 24.8, and let's times by 16.05. And I believe you only get 2 sig digs because 25 liters only has 2 sig digs. So I get an answer of 16. Anybody else get 16? So here's what I've shown you today. We now have a way to figure out how heavy gases are. Does that make sense? Previously,
Tyler Archibald, please come down to the office. Tyler?
Previously, we were able to work with volumes of gases, temperatures of gases, and pressures of gases. Avogadro, his theory basically was that any gas, it doesn't really matter what it is, it has those characteristics based on how many molecules there are. So if this gas has 10 molecules, then this gas over here probably also has 10 molecules. And I don't actually care what variety of gas it is, whether it's carbon dioxide or methane. Based on that, someone else was able to figure out, well, if we know how many molecules or how many moles we have, we should be able to figure out how many liters it takes up. And so using 2 different relationships, this one right here is like a balancing type relationship. Using this relationship here, which is like the molar equivalency relationship, and combining that with the relationship you guys had previously learned, which is like the grams per mole relationship, we can now do a lot of unit canceling. I really prefer trying to show it like this because I even try to teach kids how to do this when they're in grade 10 because I know that these skills are hopefully useful the further along you go because you guys can all see how stuff cancels? Good, okay. So, does that make sense? Okay, let me make up one more example because I feel like maybe 2 examples isn't quite enough. So can I just randomly make one more up just for practice here? Do you guys know what ammonia is? NH3 is ammonia. Ammonium is NH4. So why don't we work with NH3 gas, ammonia gas. So I'm going to say that NH3 is going to decompose, and I'm going to pick like the mass of it because I want to work on our mass conversion. So why don't we say that there's, I don't know, 12.1 grams of NH3 decomposes. I'm going to ask you to find the volume of, let's say, a hydrogen gas made. So when I give you a question like this, you'll probably recognize it at first because you get one number. Either the number will be a grams number, or the number will be a liters number, and you're only getting one number, and it's your job to convert not only a type of gas from one type to another, like for example in this one here we're starting with ammonia and we want to finish with hydrogen, but the other problem is we have to convert the type of units. I gave you mass, and I'd actually like to try to calculate volume. Does that make sense? You guys want to give this one a try yourselves? Give you like a 5-minute head start or so. I'll still do it with you guys, but I thought maybe it's worth it if you guys try it yourselves. Look back at the last example we did. The first thing you need to start with then, you need a balanced equation. Before you do anything, find a way to write an equation for NH3 decomposing. If something decomposes, it breaks up into like its elements. So that's N's and H's. Would you just write it just like that though? What do you need to do? Good, yeah. Add 2's to both of them, because nitrogen comes in groups of 2's and hydrogen comes in groups of 2's. So now we can balance. Oh, you know what? You asked a really great question. I didn't give you some information that's really important. Why don't we make it at STP? Good question. You do need that information, otherwise you don't know that middle ratio. Good catch. Thank you. So if you're stuck, here's your balance. So now you're at the point where you can probably start writing out a line of work. Start with 12.1 grams of NH3. When you're done, you want to try to find a way through different ratios and canceling to make it have liters of H2. So you're probably going to have multiple different ratios along the way in order to do that. Give you a few minutes still to try it yourself. Anybody able to get an answer? What'd you get?
67.
Anybody else? 201 as well. Anybody at the back table? Did you guys get anything yet? Okay, let me give you like 1 more minute just to try here, and then I'll walk you through the right solution. Let's see who's right. Okay, hopefully you are able to understand though that you're going to have multiple different ratios you have to deal with. To be honest, it doesn't matter which one goes first. What did you guys do first? Like, what was the first thing you tried to ratio away? The grams or the NH3? Okay, that's valid. We can do that first. So if you want to do that, I'm going to go NH3 goes here, and we want H2 to go right here. So that means you need to put a 3 on top and a 2 on the bottom. Is that okay? You don't have to do that first, but you have to do it at least at some point. This will have to cancel. Okay. At another point, you're going to have to put grams on the bottom and put moles on top. The issue is we need to use the molar mass. You have to make sure you use the molar mass of the right thing, though. This grams right here was of NH3. So you have to use NH3's molar mass, not hydrogen's molar mass. Did anybody use hydrogen's molar mass? Okay, that's where your mistake would have been. It's okay for you to do the ratio first, but keep in mind that the grams was originally attached to NH3. So you got to do NH3, so that's 14.01 and 1.01 times 3. That's your molar mass you need. So it's 17.04. And that goes on the bottom. So again, it doesn't matter whether this ratio was the first one you used or the second one you used, but make sure you use the right species molar mass. I don't know, species is the wrong one. Use the right reagent molar mass. Because if you use the wrong molar mass, obviously the whole thing is buggered, right? And that should cancel out your gram symbol right here. And then for the last little bit, we need to do like a liters and a mole. And Talia made a great point in asking me what conditions, because it makes a complete difference, right? And so at STP, the conditions were 22.4. So those are the 3 ratios you should have had. I don't care what order you put them in, that doesn't actually make a difference. But make sure you have those 3 and make sure you have the right molar mass. All right, let's try it again here. 12.1, I'm going to times by 3, divide by 2, also divide by 17.04. And then times by 22.4. I got a 23,859. So actually, nobody who gave me an answer was right. Because I had 23.85915. That was the right answer. So with SIGDIGs, it's going to be 23.9 liters of hydrogen. All right, so where'd you guys mess up? It sounds like a few of you did the wrong molar mass. You just didn't type it in the calculator, right?
Yeah.
All right. Any other issues or mistakes that... What was that? So you used the wrong molar mass. Okay. Okay. One last comment, and then I think we can probably take off for the day. This is kind of the end of the gases unit, believe it or not. We've only got one more topic tomorrow. The topic tomorrow is called the ideal gas law, and the purpose behind it is to help with calculations using this step right here. Give me one more minute, guys. That 22.4 liters per mole is at STP conditions. We also have a number for SATP conditions. However, in real world scenarios, is everything in life going to either be at 0 degrees Celsius or 25 degrees Celsius? Isn't that a huge gap in terms of solving a problem? Where it's like, well, I mean, what if something blows up at 100 degrees Celsius? I mean, to be honest, when something combusts, I doubt it happens at room temperature. It's usually quite hot. And so tomorrow what I need to do is I need to show you a method in which we can find this relationship, because it's not always actually 22.4 or 24.8. Depending on temperatures and pressures and volumes that you have involved, it might actually be a different relationship. However, the basic work I taught you today will still apply. You're still going to need to have like a ratio based on volume. You're still going to need a ratio based on like grams to moles. You're still going to need a liters to mole relationship, but it may not always be one of those numbers. So that's tomorrow's lesson. And basically after that, we're done the unit. It's actually a very short unit altogether. So that's tomorrow. Friday's a work day, plus it's Halloween, so I don't know what we'll get accomplished then. And then next week, well, it's blunt, right? And then next week, we have 2 labs and a quiz. And the following week, we have our unit test. And then that, I believe, is on the like 2-day week that we have. Any questions? Cool. Okay. There's like 5 minutes left, so whatever you guys need to do in 5 minutes.